All right, so in class we already talked a little bit about hashing last time. What I want to do is give you now a little bit of background of what hashing is and why we use hashing. So as a first part, um, what is hashing? Well, essentially all that it is you take a message M that is text, has an arbitrary length, and the output is a hash of the text, or you can think about it as a digest. The important part is that no matter how long the input is, the output, that is the hash or the digest, is of fixed length. Now, what are the properties that we're looking for? The first thing is it has to be deterministic. That means that the same message will always generate the same digest. The second, it has to be fast, meaning that when I give you a message and I do a hash of the message, it should be very simple and very fast to compute the particular hash. So you shouldn't need many computing cycles for it. It should also be unpredictable. So if you have two messages, M and M prime, that are similar, then these hashes of these two messages should look very different. And it should not be invertible. That is, you cannot find so-called inverse functions, so that there's a functional form such that when you get the message, when you get the hash, you can invert from the hash what the message was. That's important because when you have a message M, or rather when you get a hash, you don't want to have the possibility where an attacker can find another message in normal time. Now, in normal time in number theory is referred to as polynomial time. The opposite, or is non-polynomial time, something like exponential time. So that means the more you want to try to find out, you have to use exponential more time in order to get the result. Finally, you want to also have something which is collusion resistance, so that an attacker cannot find two messages such that the hash of the messages coincides in normal time. I want to be very clear that when you have a fixed output, which is what a hash produces, then there is always the possibility that two messages will give you the same hash. Now, just think about this for a second. That sounds like something that's highly unappealing, but I'm going to give you a few examples of hashes in a minute. The one that is most commonly used is the Shaw 256 hash, which gives you an output of 64 characters. Now, 64 characters means that for each of these digits, if you want, of this hash, you have a fixed number of letters and numbers that can go there. So you have 24 letters plus you have the 10 digits of the numbers. If you add this all up, the number of possible permutations or combinations of letters and numbers that you have is finite. However, text that you are trying to hash, there's an infinite number of possibilities there. So therefore, it is always possible that two texts give you the same hash. The important part is that it is not easy to find two of those messages. All right, now let's give a simple applications. Where do we actually see this? Number one is, for instance, databases that store user passwords should always store only the hash of the password, not the password itself. So that when you log in and you provide your password, the process of logging in creates a hash, and then you compare the two hashes. Now, why is that important? Well, some attacker enters your database and snoops around the data. If the data, like your password, is stored in plain text as opposed to as a hash, then the attacker can go out and immediately impersonate you. Now, here's some nerdy stuff that you need to know. Just for some background, if you're really keen, read something about P versus NP hard problems. The idea is essentially the following question. It's an unsolved problem in computer science. If a solution to a problem is easy to check, is it then also the case that the problem is easy to solve? Easy here refers to polynomial time. So P problem is a problem that can be solved in polynomial time. An NP problem is one that cannot be solved in polynomial time. And we do not know the answer to that question yet. It's one of the Millennium problems, which, if you solve it, gives you a prize of, I think, $1 million. Something like. Now, what hashing functions are out there? Well, the short answer is there are many. There's something called MD or MD4. There's an MD5 version. There's Shaw. There's Shaw 256. And the latter, Shaw 256 or Shaw 256, is something that is very commonly used. it gives you an output of 256 bits, where a bit is usually 4 characters. And so therefore, this is a message which gives you 664 characters. And I think I got this wrong. I think 4 bits is a character. Sorry about that. It has been, it's a hashing algorithm which has been developed by the NSA. Yes, exactly that, NSA. And if you're keen, this code is publicly available. I post a website there. There's also a SHA 512, and there is something called the RIPE-MD, which is an improvement of the MD ones, where the 160 cents for 160-bit output. So RIPE-MD 160 and SHA 256 are used in blockchain technology currently. Now let me just give you a few examples here. Let's take hashes of my name, Andreas. You have the MD5 hash. You see then the next is the SHA-1 hash. And finally, you have the SHA-256 hash. As you can see, the number of characters in each of these hashes increases. As another example of how small changes to text matter, consider my name, where I take every, or the odd number of characters are capitalized. You see how the hashes for MD5, SHA-1, and SHA-256 are entirely different. There is no relation to it. And that basically gives you the, that they are sufficiently distinct that small changes in the text make large changes in the hashes. Now, one problem that we should keep in mind is that these hashes can be cracked. So I went to a website called CrackStation and entered the respective hashes and just tried to crack them. And as you can see, MD5 and SHA-1 were quite straightforward, were all cracked, whether or not I capitalized the letters of my name or not. Even for the SHA-256, my particular name had been cracked. Now, one of the standard approaches in order to crack a hash would be to just use a standard dictionary. It's called the dictionary tag, where you basically just run through standard dictionary entries. And my name, Andreas, is, believe it or not, it's actually a standard dictionary name. But the one where different capital letters are being used is not, so that's much harder to crack. Now, the whole point of what I'm trying to describe to you here is why are hashing functions used in blockchains? What is the use of it? The first one, it's an easy way to represent data. It's because you always get, no matter how long your input is, you always get the same output. So that's a pretty good convention to store information. The second is that small changes in the data trigger large changes in the hash. So if you recall the demonstration that I gave you, it is very easy. That makes, these large changes that will be invoked make it very easy to check consistency. And this is a critical part, is the hashes are also used as pointers. So one of the things that you do if you try to program is you always need to have a pointer in your database to point to the right entries. And the way it works is that the hash at the top of the block, which is in the header of the block, always points to the preceding block, which makes it quite easy to find data when you search through the database. Now, finally, we use hashes of hash as data storage. And in particular, that is a very convenient method in order to find information and to be able to verify that information is at a certain spot. Now, the way it is done is by producing hashes of hashes. And when you do this, what you essentially create is something referred to as a Merkle tree. This is a convenient way to identify the existence of data. And let me just briefly show you how that works. So here is an example taken from GitHub. Now what you see here is you have a number of transactions. And what you're going to do is you're going to take hashes and then concatenate the hashes and then create new hashes of those and do this repeatedly. So very precisely, you have here at the bottom of the Merkle tree, you have the transactions. Those are the leaves. And then you take the hashes of those and then the hashes of the hashes, and that they will form the branches of the tree. And when you finally have done all the combination of the hashes, you have the Merkle root, which is the root of the tree. All right. So now how is this and why is this convenient? It is a fast way how you can check whether a transaction T would be part of a particular group. And in particular, this is a very convenient and fast way to check if the person that you ask for the information of whether or not your transaction is in a group is actually legitimate, because they need to have the right information for you. So here's how this works. Suppose you have a record of transaction 2. So you know what your transaction is and you know its hash, of course. Also suppose you know the hash of the root of the tree. Now what you do is you go to the verifier or to the authority and say, is it true that my transaction, which is number 2, is part of this group of transactions? Please verify. Now, what you get as an answer then is that the verifier or the authority basically just gives you a few pieces of information. Namely, they give you, what they do is they basically return the hashes of, and now I'm going to use the pointer here. They give you the hashes of 4, 5, 6, 7. They give you the hashes of 0, 1, and they give you hashes of 3. Now, why would they be doing this? Well, the first thing that you do is when you have the hash of number 2, and then if you look at the hash of number 3, which is given to you, you can combine the two hashes together and then compute the hash of 2 and 3. Once you have the hash of 2 and 3, and you have been given the hash of 0 and 1, you can combine the two, take the hash, and compute the hash of 0, 1, 2, and 3. You've also been given the hash of 4, 5, 6, 7, and then you can just combine these two together and then therefore check if indeed the output is the hash of the Merkle tree, which is what you have. Now, why is this useful? Well, all that you need to do is you need to get these 3 pieces of information when you have your request, and all you need is the hash of 2 and of the root. As you can guess, this is quite a straightforward way how you can collect the data and how you can store data and how you can transmit information.